I am going to tell you everything. See, it says it right there, everything. Everything you need to know about gravitational potential energy. So that includes how to use gravitational potential energy near the surface of the Earth for like a dropping ball right here. That's what that picture stands for. And how to use gravitational potential energy for bigger systems like with a asteroid falling on the Earth, or a moon orbiting the Earth, or the sun with another sun, or something like that. Real stuff. But with that, we need to start somewhere. And we're going to start with a couple of ideas. Number one, the work energy principle. The work energy principle says that if I have some system, and it's important to have a system, and I'll talk about that in just a second, then the work done on that system is equal to the change in energy of the system. Okay, well, fine. Well, then what is work? Well, work is defined as a force over some distance. So we write that. Let me make a point right here. I am going to be doing this in terms of not using calculus. So this is the algebra-based version of everything you need to know about gravitational potential energy. And I am going to use some Python stuff here too. So I'm just letting you know, there's going to be Python. I'm going to do some coding stuff because I like to do that. Okay, back to work. So this is the force and displacement. So F is the force. Delta R is the displacement. They're both vectors. So this is the vector dot product. And it gives you a scalar value. You could also think of that as the magnitude of the force, F, the magnitude of the displacement, delta R, and the cosine of the angle between F and R. And we're going to do an example, so don't worry about that. Well, fine. Then what about energy? Well, if I have just an object as my system, just one object, then the only energy I could have would be kinetic energy, and that's going to be 1/2 mv squared. Okay, so now what about the force? Well, if we're on the surface of the Earth, then we're going to use the gravitational force, and it looks like this. F, I'll call it Fg, equals mg, where g is the gravitational field on the surface of the Earth, and it has a value of g equals 0, -9.80 newtons per kilogram. Yes, that's the same thing as meters per second squared, but I like to say newtons per kilogram because it's a gravitational field. Okay. So that's work, that's energy, this is a change in energy, and that's the force. Let's just do a very simple problem. Here I have a ball of mass m, and I'm going to let it drop a height h. And I want to know how fast it's going down here. So let's call this position 1. Let's call that position 2. So what's v2 equals? And let's say let's say for now v1 is equal to 0 meters per second, even though it doesn't really matter. So how could I use the work energy, and why would I use the work energy principle here? Because if I don't care about time, which I don't, then it works better to use the work energy principle. You notice I used work twice? That would look bad if I wrote it, but when you say it, it's okay. So I'm going to go ahead and use the work energy principle to solve this problem. How fast is it going at position 2? So the first thing I need to do is say, what's my system? And this is something that a lot of textbooks kind of gloss over, but it is very important because what you declare as your system tells you what kind of energies you have. And if I say my system is just a ball, then the ball will just have kinetic energy. And yes, it actually could have other types of energy. It has, it could be hot, it could have thermal energy, it could have vibrational energy, but let's just say it's a simple case. It's just a point mass, it's a dropping ball, that's it. So that means I only have kinetic energy. And now I need to find the work. To do that, I'm going to draw a free body diagram. It just looks like this. So there's mg. That's the only force. And then I need to find the displacement. And so the delta R in this case is going to be equal to, I'll write it as a vector, 0, -h, 0. Right, because it's going to go from here down to there. That's in the h direction. You'll notice that it doesn't matter where y is equal to 0 because I don't even care. I don't care about what the y position of this is. I care about the displacement. This is important, and it'll come back later. Okay, so now I know delta R, I know force, I can calculate the work, and I know the change in energy is going to be kinetic energy. So this says the work is going to be equal to F dot delta R. That's going to be, we can actually write that as F delta R cosine theta. And in this case, what's theta? Well, if we're moving down and the gravitational force is down, they're in the same direction. So theta is 0. The cosine of 0 is 1, so this is just F, which is going to be mg, and delta r, the magnitude of delta r is going to be h. And now you may be thinking, hey, wait, that negative sign, what about that? Well, actually, if you do the dot product and I multiply these components together, 0 times 0, and then a negative y component times a negative y component there, I get a positive. So it's going to be positive, trust me. But that's the work done by gravity, and that's going to be equal to the change in kinetic energy. Let's say delta K, it's going to be K2 minus K1. So I can say mgh equals K2, which is 1/2 mv2 squared minus 1/2 mv1 squared, and then I can solve this for v. And I'm actually going to solve it generically and then just leave it at that because I don't really care that much. The mass cancels. I can divide everything by m. Now I want to find v2, so I'm going to add that to the other side. So I have 1/2 v2 squared equals 1/2 v1 squared plus gh. Now I'm going to multiply both sides by 2 and take the square root. v2 equals the square root of v1 squared plus 2gh. And that's my answer. And you can put some numbers in there, but I don't really want to do that. All I did was a work energy problem using the gravitational force. Now, what about potential energy? I thought this was all about potential energy. So it turns out that let's do another problem. Suppose that I have some magic track, and I start with the ball right here, and it goes down over here, and then it goes over here, and that's the same ball, and this is a height h, and this is an angle of, let's say, alpha. I don't know, I just picked that. But this is h. Okay. Now, I want to start here at v1, and I want to appear at position 3, but I'm going to go through position 2. So I want to go from 1 to 2 to 3, and I want to find the final speed. And so just imagine this track. There's this ball sliding without friction down the track. It gets down here and it turns, and there's forces on the ball, but there's no frictions, there's no energy loss. And I want to find out how fast it's going. Same mass, same height, and everything. So what's V3? So let's do it again. System of just the ball. And I just want you to know, I'm not putting a time limit on this video. This video may actually go on forever. And if you don't want to do that, then just bail at any time. Come back. Bail and come back. I'm fine with that. I won't even know. I promise you, I won't even know if you left. And if you did leave, you wouldn't know what I say now because you just left. Okay, so the system of the ball, so I need to do the work done on the ball. Now, in this case, this is on a track. So right here, there's actually two forces. I have this one, the gravitational force, and then I have some normal force the track needs to push up on the ball. So I'll have two works done. So the work done is going to be equal to the work done by gravity. Now, in this case, the work done by, okay, actually I need delta R. Let's get delta R. Delta R is going to be this vector right here. Okay, so if that's the angle theta, then let's call this distance S. So this is going to be equal to, I'm trying to think if I should write it as a vector or just as a magnitude. Let's try writing it as a magnitude, S. Let's just do that. Okay. We don't know what it is, and it's fine for right now. Okay, so then the work done by gravity is going to be equal to work done by gravity is going to be the gravitational force, mg, times S, times the cosine of theta, where theta is the angle between mg and S. So here is this. That's the direction of S. And this is the angle, the same angle as that. That's the angle alpha. So this is alpha C, the complement of alpha, right? Because you could also look at it this way. If that's alpha, that's 90 degrees. That's the complement of 90 degrees. Is that okay? That should be okay. Okay, so the complement of theta, or theta is going to be alpha C, which is the complement of this, so which is the same as the sine of alpha. So this is going to be mgs sine of alpha. Cosine of alpha C is the sine of alpha. Okay, now what about the work done by the normal force. So in this case, work done by normal force is going to be the normal force, which I don't actually know the magnitude of it. I don't really care. I could figure it out. Times cosine of the angle between the normal force and S, which in this case is 90 degrees. And the cosine of 90 is 0. So the work done by the normal force is 0. Okay, so now I just need an expression for S. So if this is a triangle, I can say S times sine of alpha is equal to H, right? Because if this sine is opposite over hypotenuse, and so that would be H. So sine of alpha times S is H. So that means the work done by gravity is mgh. Isn't that awesome? Okay, now that's just going to part 2. And now I need to go from 2 to 3. So here along this path, I have the normal force pushing up and the gravitational force pushing down, but I'm moving that way. So in that case, both of the works done are 0 because they both are forces perpendicular to the direction of travel. So the total work done is going to be mgh plus 0 plus 0 plus 0, right? This is the normal force right here, the work done by that. This is the normal force on that other path, and that's the gravitational force on that path. So the total work is mgh, and that's going to be the change in kinetic energy. So I have mgh equals K3, 1/2 mv3 squared plus 1/2 minus 1/2 mv1 squared. And you can see we're in the exact same position we were before, such that v3 is going to be the square root of v1 squared plus 2gh, the same speed. So the important point here is that the work done by gravity does not, well, I just showed you 2 paths. If I do this path and I do the work done by this path, it's the same thing. In fact, even if I did this path, which I want to do, but I'm not going to, the work done along this curved path, which is actually difficult to do, is also going to be mgh. The work done along this path, mgh. In the case where the work done by a force does not depend on the path and only depends on the endpoints, we can take that work done and move it to the other side of our work energy equation and call it a potential energy. So I had this. The work done by gravity is a change in kinetic energy. So if I want to, I can move it over here and I could say 0 equals negative the work done by gravity plus delta K. And I can call negative the work done by gravity equal to the change in gravitational potential energy. So in this case, I know this is negative mg delta y. No, that's not. It's actually going to be mg delta y, right? Because I said it's actually delta y was in the negative y direction. So it's mgy. So mg delta, the change in gravitational potential is mgy. Now, we will often say this. UG, the gravitational potential energy, is mgy, and that's fine. Okay, so that gives us the change in gravitational potential is mg change in y. This is meaningless. You're never going to see just gravitational potential energy. It's always a change. And so that means that when you do a work energy problem, let's do that same problem one more time. Here's the ball falling. This is position 1 and position 2. I can say my system is now the ball plus the earth. And that means that, because in fact, you can't have a potential energy associated with just one object. It doesn't make sense. It has to be interaction between 2 objects, and that other object is the earth. So in that case, if I have the earth as my system, I do not have work done by the gravitational force because that's an internal force, and instead I have potential energy. Now be careful. You cannot have work done by gravity and gravitational potential energy. You can only have one or the other. So if I have just the ball as my system, work done by gravity. Ball plus earth, potential energy. So here I'm going to have work is a change in kinetic plus a change in potential. And in this case, there's no work done as the ball falls. So I have 0 equals a change in kinetic. Let's just say 1/2 mv2 squared minus 1/2 mv1 squared plus a change in potential. mgy1 minus mgy2. But no, y2 minus 1. Right, fine. It's the final minus initial. So here's an important point. Well, what's the y2 value? And what's the y2 value here? I could pick y equals 0 right down here. If I did that, then my final potential is going to be 0, and my initial is going to be negative mgh. I could also put y is equal to 0 right here. If that's the case, then this is going to be 0. But the final potential down here is going to have a y value of negative h. So either way, I'm going to get this whole thing is going to be negative mgh. Okay. Now, you could pick any location for y. I could pick it in the middle, right? And I'm still going to get the change in potential is negative mgh. So pick a place that works for you. Okay, so that's gravitational potential energy on the surface of the Earth. The important thing here is that this work done by gravity that allowed us to do it as a gravitational potential energy was a constant force. So it's easy to calculate the work done by gravity. So what about a situation where it's not so easy to calculate the gravitational force or the work done by the gravitational force? Let's say I have the Earth, and over here I have a rock of mass m, and it starts at a position r1. And I'm going to let it go. So it's going to fall down towards the Earth. So there's a gravitational force on the Earth, Fg. I'll put it as a vector even, like that. So in this case, if I wanted to do the work done by this force, it's not so easy. Because since these two are further away, I have to use the real gravitational force. It has a magnitude, Fg equals g, mass of the Earth, mass, over r squared. And as it gets closer to the Earth, this gravitational force changes. So I can't do work done by gravity as just one step. I can't do that. So let's do this problem in the following way. Let's pick some values. So I have the mass of the Earth. I need to know what that is. I think it's 5.972 times 10 to the 24th kilograms. The mass of the object, let's say it's 100 kilograms. It doesn't really matter. I need the radius of the Earth, because that's where it's going to stop. The radius of the Earth is 6.3 times 10 to the 6 meters. The gravitational constant G is 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. So I can calculate the gravitational force. And here's what I'm going to do. I'm going to break this into small parts, small steps. And over each one of these steps, I want to assume that the gravitational force is constant. So let's say delta R is going to be equal to, I'm going to pick some value, 100 meters. Oh, I need to start R1. So R1 is going to be equal to, let's say it's 2RE. It's twice the radius of the Earth. Okay, so this is, it didn't draw it that way, but that's fine. So it's twice, so it here to there is 6 million meters, here to there is 6 million meters. So I'm going to break this into a distance step of 100 meters. And then I can calculate delta work done by gravity. It's going to be equal to this force, G, ME, M over R squared times delta R. And it's going to be positive, right? Because it's moving in the same direction that the gravitational force is pulling. And over this, R is not going to change that much, so I can assume it's constant. And then what I can do is do it again, right? So what I'm going to do is let this move right here, calculate the work. Now it's going to have V1 equals 0, V2 is some value. I can do the work energy problem again right there and calculate it again. So for each step, I can say delta work is the change in kinetic energy. The delta work I can calculate this way, and the change in kinetic energy is going to be 1/2 m v2 squared plus minus 1/2 m v1 squared. So if I want to go 6 million miles in steps of 100 meters, it's a lot of steps, and I don't want to do that. I don't want to do that by hand. So instead what I'm going to do is to you have a computer do this. So I'm going to start up here, move, calculate the new speed, move, calculate the new speed, and so forth. Okay, so let's jump into this and do this in Python. If you haven't used Python before, just hold on. It's fine. Everything's gonna be fine. Okay, so I'm using GlowScript V. It's Web VPython, and this is in Trinket. It's a web-based environment so that you don't have to install anything. So I'm just gonna go ahead and jump right into it. If you're not comfortable with all this, it's fine. We'll catch things up later. If you ask questions, if you have something that you don't understand, then we can do that. I want to make a graph of the velocity as a function of time. So I'm going to plot, no, velocity as a function of position. Let's do that. So let's just go ahead and start off with that graph, and then we can do our calculation. So I'm going to say G1 equals graph. Graph is an object in a Web VPython. I can give it a title, call it falling rock. I can give it an X title. X title equals R in meters. I can give it a Y title, and it's going to be equal to V in meters per second. Let's give it a width, spell it correctly, of 500 and a height of 250. This is the width and height of the graph. Now I need a function to plot in that graph, so I'm going to say F1 equals G-curve, color equals color.blue. I like blue. I don't know why. Blue just always works for me. So now let's put our constants in there. G equals 6.67 times 10 to the negative 11th. ME equals 5.972 times 10 to the 24th. I'm not putting units in there, right? Because if I put my units in that number, then when Python tries to operate with that number, it's like, I don't know what you're doing. And so you can't do that. Okay, the radius of the Earth, RE, is 6.3. Is it 6.3? Radius of the Earth in meters. It's 6.378. Okay. 6.378 times 10 to the 6th. The mass of the object is 100. And then I'm going to say R equals 2RE. That's where it's starting. I need to also start with an initial velocity. So I'm just going to say V equals 0. I need my step size, dr equals 100. I said that. 100 meters. Okay. So now let's do this. While r is greater than re. So I'm going to keep moving until we get to the surface of the Earth. And now the first thing I want to do is to calculate the gravitational force. I'm just going to calculate the magnitude of the force. So I'm going to say F, let's just call it F. It's G times ME times M divided by R squared. And if you're not familiar, in Python, squared is star number, not hat. Okay, so now I have that. I can calculate the piece of work during that step. dW equals, it's going to be equal to F times dr, right? Because dr is moving towards the Earth, which would be down, I guess, this way. And the force is too, so they're in the same direction. So it's a positive number. I calculate the magnitude of the gravitational force as a positive number, and then dr is a positive number, so the work is dr. Now, what about the speed at the end of that? So let's find the new speed. So I should have written this down, but I didn't. This is going to be equal to the change in kinetic energy. So I can solve for the final velocity as this. V equals square root of the work done, dW, plus, no, it's 1/2 m, so it's 2 times dW divided by m squared. Okay, let me write it on paper because I'm going to make a mistake. Okay, so in that step, I calculated delta W, and I want to find V2. So I'm going to add this to both sides, and I get 1/2 m V2 squared equals delta work plus 1/2 m V1 squared. Now multiply both sides by 2 and divide by m. V2 squared equals 2 delta work over m. Can't see that, sorry. Plus V1 squared, and then I take the square root of both sides. Okay, so I don't square it. Yeah, good thing. Good thing I did that. Okay. switching back to the code. Switching back. Okay, so here we are. So it's 2 dw over m. Is this big enough for you to see? I hope so. I guess I can make it bigger. Plus v squared. Now, here is something weird. You'll notice that I have v and v. And so what Python does is use this as a make equal to sign. So it takes the initial velocity, squares it, adds this thing, takes the square root, and then makes that the new velocity. So I don't have to worry about v1, v2, v3, v4. I can just say v. I just updated v. So when it gets back to the loop again, it's going to start with that value of v. So now what I want to do is to plot this. So I'm going to say f1.plot r and v. And then what I want to do is to move my r. So I'm going to say r equals r minus dr. Right? Because if I start it really high up, I want to move down a position. So I need to subtract that 100 meters because I'm going down closer to the surface of the Earth. This should work. I don't know. Might have an error, but it might work. Let's just do this. Print v equals v meters per second. This is how fast it's going at the end. So I'm going to run it. Let's see what happens. And I got an error. Aha, I know what I did. Okay, 2re. It's 2 times. Python doesn't understand what you mean when you just say 2re. It's like, I don't know what you're talking about. I knew it. You know what I meant. We all knew what I meant. Okay, but Python didn't know. And there you go. Okay, so it starts out here at this. I'm sorry. It starts over here. It starts over here at and then it goes down this way. And then so here's the final position at the radius of the Earth, and it's moving at 7.93 times 7.88 times 10 to the 3 meters per second. Let's make another graph. I want to plot the kinetic energy as a function of the height. Let's try that. So let's say change this not to the velocity, but k in joules. And so down here I can calculate that. K equals 0.5 times m times v squared, and then I'm just going to plot that. K. Check that out. Okay, so here you're starting to see as I start off, I have no kinetic energy and I increase. And so really now what I want to do is to calculate the total work done as a function of my position, because it turns out that it doesn't matter the path. I'm not going to show you that today, but if you want, I can make a program to show you this, that this work done by gravity is path independent. So I want to calculate the total work in each, add it up as I move along. So let's go up here and say work equals 0. And then down here, I'm going to say work equals work plus d work. And then I'm going to plot, I got to change my title, work, let's just call it work versus r, and I'm going to plot work. Okay, so it looks the same, right? Because the work done is the change in energy. Now, if I want to make this a gravitational potential energy, then I just need to make it negative, right? That's what we said before. So let's just plot, I can even call it u, but that's fine, negative. And this is the gravitational potential energy as a function of position. And there's some really important stuff here. But first, if you were able to write this as an equation, let me write this as an equation, which, I'm going to write it down as an equation and show you that it's the same thing. So it turns out that the gravitational potential energy for real gravitational objects looks like this. I'm going to use U big G. It's going to be negative G, mass of the Earth, mass over R. Now, there's some important things here. So UG, as R goes to infinity, goes to 0. If I get further and further and further away, then this becomes more closer to 0, which makes sense. If I have two objects in an infinite distance away, they shouldn't be interacting at all, and there should be no gravitational potential energy. As R gets smaller, what happens to the potential? as R decreases, the gravitational potential energy decreases, right? So this is kind of a weird thing because we always have the change in gravitational potential energy that matters, and here you're seeing this as R. This is actually very useful to do, but this is technically the potential energy with respect to infinity. But let me show you that this does indeed work. I'm going to make another plot of the negative the work, and I'm going to calculate this equation like this, and then we'll do, and then I'll show you something important. Okay, so over here, I'm going to say U equals negative G times mass of the Earth times M over R. And now what if I plot that? Let's make another plot. F2 equals G curve, color equals color dot red. And then down here, I'm going to plot F2 dot plot RU. Let's see if that works. And they're different. Why are they different? Are they different? G, M over R. R negative W. I wonder if because my step size is too big. Oh, it got mad now. No? Why are these different? So this one starts off at 0. So this is starts off at, oh, you know what? No, I have the same values. Why are these different? Oh, that's why. Okay, so the reason is that I'm calculating the work done from some finite position here, and this is the potential energy with respect to infinity. So that's the problem here. What I need to do to make these two work, and in fact, I don't need to make these work. What if I define my system as the ball plus the Earth, and I want to plot the potential energy, the kinetic energy, and the total energy? So that's what I'm going to do. So let's go up here and call this one the total, label equals total energy. This one I'm going to call kinetic, label equals, kinetic energy. That's called kinetic. And then let's make F3 equals G curve, color equals color dot green. And this will be, let's just call this potential. Okay, so down here, I have K, I have U. I want to plot K, U, and E. So let's just calculate the total energy. E equals K plus U. And then F1 is the total energy, so it's going to be R and E. F2 is the kinetic energy, so K. And then F3 dot plot is R and U. And let's put this back at 100. And I'm trying to think if I should animate it. I don't think I will. Let's just plot it. So this tells me exactly what I need to know. Notice first that the total energy is constant. Because if I have the system of the ball and the Earth, there's no work done on the system. So there's no change in energy. So the change in kinetic plus the change in potential is 0, which means that K plus U is constant. And so now as I fall, remember I'm going from this way down, which I maybe should animate it. The kinetic energy is increasing and the gravitational potential energy is decreasing. And those two added together is a constant value. Okay, now I want to show you one more thing. Let me just plot the potential. So I'm not going to plot these two. And so what about the other version of potential, mgy? How do we make a connection between mgy and this? Well, mgy says that increases in a value of y would increase the potential by proportional amount, mg. It's a linear function. And you'll notice down here that if I zoom in on just this area, it is very linear. It looks linear. So it's an approximation to say that the gravitational potential energy is linear just because we're in this small region of space right here. So that's why. Okay. So potential energy is mgy is just a cheat, but it works. It works. So that's that. Okay. I think that's enough about gravitational potential. I said I'd tell you everything. I didn't tell you everything, but I did show you how to derive the gravitational potential energy and the two different forms of gravitational potential energy. So hopefully that helps. If you have any questions about Python, let me know down below. I'm going to give you this code. Hope you like that code. And that's that. I'm going to save it. Talk to you later.